This is our lecture number 8. We're trying to look at the problem of analyzing programs from a practical perspective, not forgetting the theoretical understanding of this domain. As programmers, we know how to write the code, but then there is another group of people who are interested in looking at this code and making some decisions about that code, which may affect the way the code is executed, the way the code is optimized, the way the code is maybe highlighted for the programmer as a broken code. So these are just another group of people than programmers. If you are thinking about yourself as a programmer, then you will probably be writing code. You will be the one who produces this code. But you may also be in the future in the second group. So you may be one of those who write the compilers, for example. And when you write the compiler, you have to create something which we study on this course, some sort of an analyzer which will look at the code, analyze the code, and make some decisions about, for example, what would be the better way to run this code on the to present this code to the computer so that the computer can run it the best way. So symbolic execution, the topic number 8. It is one of the most important principles, ideas, concepts of how the code can be analyzed without being executed. As you remember, we discussed the dynamic analysis. It's only one approach when you run the code in order to see how it works. All other approaches, all other ideas which we discussed before and will discuss in the future, they are about looking at the code and making decisions about it without running. Like, for example, data flow analysis, which we discussed on the previous lecture. You don't run it, you just look at the control flow graph, and then you go through these blocks on the control flow graph, and you make the decision what's the possible outcome of each block, and which data can arrive at certain blocks, and so on. So symbolic execution is something also very interesting. I decided to break this lecture down into 4 parts. First, we're going to see the theory, so how it should work. What's the theory of symbolic execution? I think you just need to understand it, how it theoretically looks, how it's supposed to be. And then the practical experience, which I collected myself a little bit, and so I know some people who work in this domain, so they also provide me some information how it works, what happens in practice. The theory is one thing, the practice is a different thing. Then we're going to look at the test generation, one of the practical application of symbolic execution. So why it's used, not only to analyze the code, but also to create the code. And the final one is concoling testing, so-called, which is also a pretty practical approach where symbolic execution is used. Okay, so let's start with the theory. So what is symbolic execution? Theoretically, it is this way. So if I need to formulate it in just one line, then symbolic execution means executing the program without actually running it, but on a paper. So you take a piece of paper, you create this control flow graph, which you can see right now on the screen, and you just, without asking the computer to go through this graph, without letting the computer run the instructions, you just go through the graph on a paper. Of course, there's going to be a computer, there's going to be some algorithm, but this algorithm will not do the actual calculations. The algorithm will just make decisions of what will happen if we can imagine the real execution happens. This is why it's called symbolic it's called symbolic execution, because I will show you just in a few slides why the name symbolic execution. But for now, just remember, there is no actual execution. It's like a fake execution, which doesn't really happen with the computer. So look at the program on the left side of the slide. It's a simple function. It accepts the variable x. So the first line, it multiplies x by 2, assigns it to a. You probably understand the syntax. It's let's say it's C code or C++ or Java, whatever. Then it gives the a minus 4, and then if a is equals to 0, so there's the block which, so it does the validation for the 0 in order to, you understand why, in order to avoid the division by 0 here. So that's the code, which doesn't really do anything useful, but it will help us understand symbolic execution. So I created a control flow graph for this code. The first block, multiplication. The second block, the the subtraction, and then the comparison for the 0. And if the comparison is true, if it's going to be here, then the error will be issued by the computer. So now the question is, we want to understand whether this function will ever possibly reach this position. So will we ever see an error if we run this code? If I run this code with the number, let's say, I don't know, number 0 here. So I put the number 0, I run the actual test, and there will be no error. So there will be the real result here. I mean, the number will be returned from there, but no error will happen. If I run it with the number 1, again, no error. So I don't know how many times I need to run it. Maybe I can even ship it to the user, put it to production server, and just wait. And then in a few months of work, the customer calls me and say, hey, we got an error. But on the testing side, I didn't manage to find the error because I tried with number 0, with number 1, and then I gave up and said, okay, let's try number 5, number 6, number 7, number 8. I mean, of course, in this simple function, I'm not going to do that because I can intuitively understand what is the number to provide. But imagine this function is much bigger. Imagine there's like 200 lines of code here. And then, of course, you don't really, it will be hard for you to understand where the error is and why will it happen and on which condition, what's the input that will trigger the error. So we can use symbolic execution, which can tell us what is the X, what is the X that has to be provided to this function so that the so-called feasible pass will happen. So the pass is feasible. It's on the graph you see with the bold line. So this is the feasible pass. Like I showed you before, we're coming in here, then there, and then this, and then we get to here. So this is the pass. There are basically two passes in this program. There's one, and there's another one. So this is, we can call it pass, I don't know, A, and this is pass B. So the question is whether the pass is, a pass is feasible, not the question, but the definition, the feasibility of the pass is that if there exists some X, that, I don't know, X, for example, in this particular case, you can see that X is 2, that will make the pass A feasible. So the question to answer is whether the pass we're looking for, which goes to the error, is feasible or not, and on which input, because just saying the pass is feasible and yes, we're going to get the error is not enough. Because the programmer, if we create such an analyzer which will just tell us that the pass is feasible, the programmer may not trust us and may have questions whether it's, because the question will be, why do you think so? And if the analyzer cannot prove it, then there's a little value in such an analyzer. So pass is feasible, one of those two passes, A and B, whether both of them are feasible or only the pass B or only the pass A. So pass B is feasible. We can see it because, I mean, we can provide this number 0 here and we can see that the pass B will just go through. The question is mostly about pass A. Pass is infeasible if it will never happen. So look at this code. It's a little bit different code from the previous one. Read the code on the left. It takes the X as an input, it multiplies X by X, and then it says if A is less than 0, then raise an error. So basically the pass is, here you see the letters A, B, C, D, so there are basically two passes, A, B, C, if it's a vector, and another one is A, B, D. And let's call this as pass 1, this is pass 2. So it seems that the pass A, B, C, the pass 1, is infeasible, because it will never happen. So again, this infeasibility must also be proven. We don't prove it now, I'm just explaining you the difference between feasible pass and infeasible pass. I hope you get it. So now we're getting to the idea of symbolic execution. So why it's called symbolic? Symbolic because it works like that. It doesn't run the code, it doesn't go through the control flow graph, it just, again, we're back to the previous code snippet, which we had before with the division by 0. So instead of providing here an actual numbers like we did before, 0, 1, 2, 3, 4, 5, and so on, and finding out that the number 2 is actually the one which proves that the pass, the bold one on the diagram on the right, is feasible. We don't do that. We don't do that because that would be not symbolic execution. That would be dynamic analysis, that would be just a normal execution of the code. We do symbolically. So we say x is equal to a symbolic variable x capital, the capital X. This is exactly what you see here. So we assign to x some symbol. Actually a symbol. It's not even an actual value, it's a symbol. And then we continue through the graph, continue imagining that in each block the execution happens. And then we do something with, and then new variables are introduced. And when we assign something to these new variables, we use the symbols instead of real values. So like here, for example, we started from x equals to x capital, and then we assign to a, we assign 2x. So the multiplication of x by 2 didn't give us some actual number, but it gave us a formula, an expression, which involves symbols, the symbols which we had in the beginning when we entered the function. Then we continue, then it says a equals to a minus 4. So we reassign a, and we say, okay, then in this case, a now is equal to 2x minus 4. Another expression, not a value, but expression. And still, we keep the symbol as a member, as a participant of this expression. And finally, we continue to this pass. So now at this point, when our machine, our analyzer reaches this block, then the analyzer see, okay, now we have we need to go into two directions, the true direction and the false direction. So if a equals to 0, so we continue in the true direction, and in this case we end up here with the two actual variables, and there are two symbols, two symbolic expressions. There they are, assigned to these variables. If they continue this way, if the analyzer continues, there's going to be exactly the same expression here. Exactly same here. The x will be also equal to x capital, and a will be 2x minus 4. So that's exactly the same. Will be attached here. So we basically attach. It's not the. I mean, there is a name for this. Different names actually I met for this set of formulas. So what would be the right name for this? For this thing which we attach to every line on the control flow graph. They call it in some places I've seen them calling that environment, or the state, or the variable state, something like that. So this is symbolic state. I would call it this way. So that's symbolic state, which is, let's say this is symbolic state, I don't know, this is symbolic state 1, this is symbolic state 2, this is 3, this is 4, and this is 5. So on each line in the control flow graph, we assign the symbolic state, which tells us what's gonna be in our actual variables, in our actual a and x, but not the data, but symbols, expressions, symbolic expressions. That's our first step of symbolic execution. Step number 1, I would call it. Go through the graph and create this symbolic state assigned to every line on the graph. The second step is so-called pass conditions. I would call it step number 2. I actually should put the numbers in the slides. It would be correct to put the number like actually step number 2. So the pass condition is a condition on the input symbols such that if a pass is feasible, its pass condition is satisfiable. So it's another thing which we attach to each line in the control flow graph. The first thing, as you remember, was symbolic state 1, 2, 3, 4, and here 5, but you don't see it here. Another thing which we attach is called pass conditions. Pass conditions. Here it means what is the predicate? What's the Boolean expression which must be true if the execution goes into this direction? So here when we start, it's just true. Just no predicate. We just say, yes, the execution will definitely continue in this direction. And then the same, no matter what, the execution will continue. So we will definitely first multiply x by 2. Then we will definitely do a minus 4. And then we will definitely reach this, this line where we compare. And after we compare, the execution will go either to true or to false. And if it goes there, then the pass condition is this. So we know at this line, we know that 2x minus 4 equals to 0. Why do we know this? Well, you can see it's clear. So we compared a with 0, and a, we know what was a was this. So we can say clearly that that we know for a fact that the computer, the actual computer, will reach this point, will reach the error only if this predicate is true. And of course we can attach another predicate to this line. We can say here 2x minus 4 will be not equal to 0. So this is predicate, let's call it P. This is predicate, this is the predicate or pass condition 1. This is P2, P3. We can call this one P4 and this one P5. That's the second step of symbolic execution. So first we went through and we defined the states. Second, we go through again, we're not executing the program. We just observe what we see in the code, what we see in the text of the code. And it's not difficult to write this machine, right? To write this analyzer, to create it. It will just go through control flow graph. Of course, the problem will be how you get the control flow graph. Then that's the first step. But we discussed it before. So let's say you have the control flow graph. Then you just go through the control flow graph, element by element, block by block, and you create these states and the predicates, the pass conditions. That's the step number 2. Then the step number 3 is, and then the question for you're still trying to add that to answer the question. So you remember the question. The question is whether this point will ever be reached. This is what we're doing this symbolic analysis for. So we're interested to know whether this pass is feasible and on which input. So in order to answer the question, what do we know about this point? What do we know about this place? We know 2 things. We know the state and we know the predicate, the pass condition. So if we know the pass condition, then we go to the constraint solver. This is step number 3. The constraint solver. The constraint solver is a tool that finds satisfying assignments for constraint if it is satisfiable. So basically we have a constraint. We have this is the state number 4, as you remember, and this is the predicate number 4. So this is what we end up having at the line, at this last line, which goes to the error block on the control flow graph. And then we ask some magic box, which we're going to discuss right now, some constraint solver, ask a question. Okay, what do you think, whether this is feasible? And if it is, give me all the values for all the symbols in the expression. And the answer will be like this. It will tell us, yeah, sure, x is 2, and this pass is feasible because this is solvable. There is a solution. So I found a solution for you. So your constraint, which you gave to me, is solvable. That's why the pass is feasible. Imagine we give this. Imagine the question is different. Imagine we don't need to know the error. We just want to know whether there is at least one normal execution of this code without an error. So we're interested in this element. So tell us, please, the constraint solver, whether the program will reach this point ever. Okay, let's try. In this case, we're going to have the state number, the state 5. State we actually don't care about in this point already. We care about the pass constraint. It's going to be in pass constraint number 5, which is going to be 2x minus 4, not 0, not equals to 0. So what do you think would be the solution? The solution could be, I don't know, x equals to 0, for example. The constraint solver will give us this. Yes, it is solvable, and here's the solution for you. Is it the only solution? Maybe not. Maybe you can give 1 as well, maybe 17. There are other solutions. In this case, the solution is probably the only one, not probably, definitely the only one. In this case, it's not. There could be others. But in both cases, we will get at least one answer, which is in most cases people are interested in. give us at least one solution. And if the program will be more complex, if the control flow graph will be more advanced, meaning larger, and there will be more input variables, then the constraint may include multiple symbols, not just one, not just X, because in this case, the solving this is easy. But in real world, you're going to have multiple X, Y, Z, and so on. And then the solving this could be a bit more complex task. But overall, that's it. That's the theory. I told you everything which you need to know about symbolic execution. This is the theoretical part. If you read the book, you're going to get something, well, something close to that. Of course, I simplified that because we don't have much time for this particular topic, but theoretically that's it. So you draw the graph. On the graph you go from top to down, marking this states, and then creating this. There could be also loops. There could be, we can discuss them now. There could be also in the control flow graph, it may return back. And then these conditions, they will become more and more complex, because every time you go on the graph, you continue, and then you make a loop, you return back to some element, and then you meet their already existing, let's say, on this graph. Yeah, let's say, I'm going to give you another graph. So let's say there's a graph which looks like this, and then that's an exit. So we know that there will be a constraint number one, pass constraint number two, and then pass constraint number three, and then we return here, and then there's pass constraint number four. So in this case, you go again, and in this case you want to, and then you want to understand whether. Let me step back a little bit. So remember the data flow analysis. On data flow analysis, we were interested to go through the control flow graph until we stop changing our meta information which we were collecting. So we were collecting information during this data flow analysis, like attaching more and more and more to the graph in order to at some point reach the so-called fixed point. And when the fixed point is reached, then we can stop and say, okay, now we have a graph with the complete information, and now we start analyzing. In symbolic execution, it's not the case. In symbolic execution, they label every line on the graph with, let's say, A, B, C, and D, and these are the labels I showed you before. And then the question for the symbolic execution is this: whether the pass, which is a vector, let's say A, B, D, B, D, C, is feasible. So that is the loop in our case, which at some point exits. So we enter the, you can see on the graph what happens: A, B, D, B, D, C. So we make one circle, and then we get out. So symbolic execution asks the question whether this pass is feasible. Maybe this one is feasible and this one is not. A, B, C, for example. That's another pass. And there could be another one, let's say A, B, D, B, D, B, D, and C. And that's another one. So symbolic execution will give you three answers. This is going to be the answer number one, the answer number two, and the answer number three. And for each answer, it will go through the same procedure. So it will, first of all, it will build these conditions, P1, P2, P3, P4. But then in order to give an answer for this long pass, it will go through this, it will basically do something like this: P1 and P2, and when we go to D, P4, and we go to be P2 again, and P4, and so on, and P3. So it will, this is going to be the expression which we're going to feed to the solver. And the solver will tell us yes or no. Yes. Sorry. It will tell us whether it's yes or it's no. So you understand the logic. So we can concatenate where we make we make a logical conjunction of these predicates in a long line in order to expect this. And here the same happened here, but I just didn't show you the true and true and true and true, just to simplify things. So let's go to the practice. So in order for this magic to work, we need to actually, the biggest problem, I believe, in this, well, not the biggest, maybe one of the problems, is how do we actually find the solutions for these constraints. So in the previous example, in the theory, it was quite easy because the expression was simple. But if the expression is longer and more complex, then people invented the solvers, so-called. So the most simple, the kind of a first level family of solvers are called SAT solvers. So SAT solver is a computer, like it says here, it's a computer program which aims to solve only the Boolean expression. So we only can give a Boolean expression to this solver, and the solver will give us the answer. So let's say in this case. So is this case, I'm trying to solve these four expressions. So what do you think that the solver will give us in this first line, the expression A or B? It will say, yeah, it's solvable. For example, A is true and B is true. That's the solution. So this expression is solvable, it has a solution. A is true and B is true. The second one, A or A and B and not A. So is it solvable? Can we suggest A and B, which would be okay for this expression, so that the expression is true? A and B and not A. So in this case, the answer is, as they say, no satisfied, so no sats, so-called. So this expression doesn't have a solution. So we may not find A and B which would be suitable for this expression. The next one, A or B or not A. Yeah, sure, we say A is true and B is true. Or we can do it this way. A is false and B is true. Actually, true, false, they look exactly the same for you, so I probably do it this way. So we can say false and B is true. That's the solution. And here, A and false or true. Okay, in this case, there's only one. That's easy. I mean, that's easy for us right now. Of course, if the expression is much longer, then it's not so easy, because it will just take more time. It's always about, the question is, in these solvers, is always about time. So if the solver has unlimited amount of time, then it can always provide you the right answer. But usually when the expression is long, then the solver at some point gives up, and at some point says, I'm not able to give you the answer within a reasonable amount of time, within a few seconds. So I will need probably a few years. And we don't have those time, so we just say stop after a few seconds. So if you take more than 2 seconds, just drop it and say, I cannot satisfy it, I cannot find a solution. So these are SAT solvers. SAT solvers are for Boolean expressions, not really applicable to practical applications, to my knowledge. So they are probably used in not in symbolic analysis, not in symbolic execution. In symbolic executions, there's another family of software products which is called SMT solvers. SMT solvers are a computer program which aims to solve so-called satisfiability modular theories. You can Google that stuff, learn it yourself. I'm not really a big expert. I just understand the idea from a high-level perspective. In these expressions, which are suitable for SMT solvers, we can use variables which are not Boolean, but they could be integers, they could be maybe strings. Usually these SMT solvers, they work with strings, Booleans, integers. I don't know whether floating point numbers are acceptable by these guys. To my knowledge, Not really. So integers are okay, strings are okay, because you can compare the string and you can do some simple manipulations with the string and the Boolean values. So look at the four expressions here. So the first one, a less than 5 and a more than 3. Probably a equals to 4 is the solution, right? SMT Solver can find it for you. So for example, you can take this SMT Solver Z3. It's a software made originally by, if I'm not mistaken, by Microsoft. So now it's open source, so you can just take it, download it, give this expression to the software, and it will tell you the answer. It will tell you A is 4. How it works inside, I don't know. You can find out. But imagine it's a black box. So within the problem of symbolic execution, for us, all we care about, it answers the question. How it does it, that's a separate story. The second question is a less than 5 and f of a is more than 42. So can it answer this question for us? Probably not, because the f is something which the solver doesn't know anything about. So it obviously can maybe suggest also a equals to 4, because it's okay for the first part of the expression. But the second part of the expression, it can't understand what to do with that. So in this case, the answer will be no, not satisfiable. This expression cannot be satisfied. The number 3, a less than 5 or a more than 10 or not a. So this is, I'm not sure whether the Z3 solver will understand that, but probably, in my opinion, the answer will also be no satisfiability, because it's a type, the conflict on the type level. So there are different types of variables. So we cannot put number 4 in here because we don't know how to inverse the 4. So we apply the operators which are applied to Booleans. But again, it depends on the solver. I'm just giving you examples to give you an idea of what on the theoretical level should be satisfiable or not satisfiable. Let's look at this one. A and false and x equals to 7. So we can say that, okay, x equals to 7 is a good value for the variable, but at the same time we say and a and false. So this is the problem in this expression. So it's going to be always false. So we scratch that and we say it's not satisfiable as well. You got the idea. You give an expression which we collected, which we assembled while going symbolically, while going on the paper. So the graph, we collected that expression, we built it, assembled it. Now we feed it to the solver. The solver thinks for some time, as I told you, for some reasonable amount of time, because usually when you take a long graph and it's very rich, so it has many diversions on the path, then the expression will be quite large, quite long, and take into account that you probably will have more than one input variables, more than one symbol in this expression, and then you give it to the solver will start doing the work, and usually you give the time constraint. You say spend no more than half a second. And then after that half a second, very often you're going to get the answer, I cannot find the solution. So give me one more year and I'll get it for you. That's an important constraint. And people actually try to solve this problem of the time by running these solvers in parallel. They're trying to use multiple cores for this, finding the solution. It's a large area of computer science. And there are many research going on there. There are many pieces of software there, like I'm showing you here, like 1, 2, 3, and many, many more. These solvers, there are even solutions which are integrators on solvers. So you take a number of solvers and then you create like umbrella solver, which knows how to work with them. And then I've heard about that. And then when the problem comes in, the expression comes to your umbrella solver, it just gives these solvers asks or tries these solvers to see how they're going to respond to this expression. And according to the preliminary result from them, a short one, they understand which one is better and they try to use that one. So they kind of, in dynamic, they try to understand which one would be able to solve this particular expression faster than another one. There are also umbrella products which try to run them in parallel and see which one, for example, completes faster. So maybe this one fails and says, I don't have enough time, but another one can complete and this amount of time. But you cannot run them sequentially one after another, because in this case, you're gonna get, I mean, the successful one may be the last one, but you will still need to spend time on the previous one. But if you run them in parallel, all 7, for example, 7 solvers, then the solver number 4 may complete within the 1 second which you have, while others will still be working. So each solver is designed usually to understand certain expressions better than others. So for example, some solver is okay with the integer comparison operators like this one, a more than 5, less than 5. And if you have many of those comparison operators, then the solver will go faster with the solution. But if you use some string operators, for example, here you can say a, let's say instead of this, you can say starts with a, that could be an expression. So we are saying is a starts with a hello. So in this case, the solver must be able to deal with strings, and it must be able to do it fast. Not every solver is okay with that. So just remember, solvers, a huge territory of a lot of solutions, which you may create another one. Many of them are open source. Some constraints are not solvable. We're going to more practical application, and you need to understand that some constraints are just not solvable by definition. So no matter, well, maybe theoretically they are solvable, by practically they're not. Like never. So not just in a few hours, not just maybe in a few years, but never. So let's take, for example, this one. So let's say this is our program and we're trying to run symbolically, and the question which we ask ourselves is whether it is possible that the program will ever reach this point. Or, okay, the question could be the other way. So let's say whether the question whether the error is possible is easy, because you can provide any password here and you can easily get to the line access denied. But the more interesting question is whether at all we can reach this point, or whether at all. So if you draw the control flow graph, you will end up with the expression with this pass constraint, which will look like this. It will look like this. This is our pass constraint, and it says that ends with H, and H is the code, the SHA code 256 of the password. So now that the constraint solver must do a reverse, calculation of this function, of the hash function, of the SHA function, but the constraint solver cannot do it. SMT solver. Not because the solver is bad, but because you understand how this SHA works, that's going to take a lot of time. It's going to take an enormous amount of time. So in this case, the solver will just give up. And there are very many examples like this. And I will show you now how this a bit more practical example, because this one is to show you the extreme case that constraint is unsolvable at all. Unless you, even if you know how this how this function is implemented, you know the code, you know how the SHA function works, everything is open for the solver, and still the solver cannot go back, cannot reverse it back. So if you say to the solver that 2 multiplied by x minus 4 is equal to 0, the solver knows how these operators work, that the solver understands the semantic of this operator, and the solver knows that if 2 multiplied by x, 2x equals to 4, then it knows how to get the x. Because this operator, the multiplication, has a quite fast to execute the division operator, which is reverse one, which can take us easily back from number 4 to the value of x. But in case of SHA, even though you know how SHA works, you know how to get from one point to another, but how to return back, you don't know. There is no function like this. So there is no supplementary function which exists for multiplication. The division is like a counter function for multiplication, but for SHA, it doesn't exist. And in many other cases, in symbolic execution, there are other situations like this. So the function to this direction exists. So how to get there, we know. How to get back, we don't. So that's called unsolvable constraints. Unsolvable, that's the keyword. Just remember it. Or, Wikipedia says almost unsolvable, or I don't know, not Wikipedia, almost unsolvable. Because actually unsolvable is quite strong word, because you can say that theoretically even this one is solvable, right? Just give us, I don't know, a few hundred years and we're going to solve it. Any password can be decrypted, any password can be returned back from the hash code, especially if this is so simple piece of here. So we are now comparing only the ends with. So in this case, maybe solution can be found in a reasonable amount of time. Maybe not, you don't need years, maybe on a fast computer you can do it in hours, because we're not looking for the entire, the full size hash. We're just taking the finally the six characters at the right. So we can actually implement a very simple, just retry cycle, which will try them one by one. And then eventually it will just hit this number, because there are not so many of them. There's 6 numbers, so you can calculate how many of them. Maybe millions, maybe but billions, but still a reasonable amount. So it is almost unsolvable. Almost. Okay, next problem. This was the first problem in symbolic execution. Second problem is called pass explosion. So, and here I can show you again a practical example. Look at the code on the left. It's a simple cycle. It assigns A to 0, and then it loops starting from 10, going down to 0, decrementing the counter, and multiplies 42 by this decremented counter, and summarizing the result. The question is whether we're gonna hit an error. Look at the control flow graph. So I can rate the control flow graph for this code, and there could be an error. You can understand why. There could be division, because it's a division, so division may end up with the division by 0. So the computer, when it will execute this code, it may hit an error here, and even though we don't have this error on the program, it doesn't in the syntax of the code, but we understand that it is a possibility. In reality, the control flow graph, it looks exactly like that, with this F line, which goes to an error. So now the question, whether this pass is feasible. Boom, 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 here and here. So this pass, which will be titled as A, B, C, D, and F, is not feasible. And it's easy to understand that, because we have if we do the symbolic execution in this direction, A, B, C, D, F, then symbolic execution will tell you that no, this pass is not feasible, because never this the pass constraint which you will attach to here, it will not be satisfiable because of the numbers and the formulas in there. But the question is more interesting, whether this pass is feasible with multiple dots inside. So if you go through A, B, C, D, and then you calculate, you do D, you say you say A, B, C, D, then you return to E, and then you return back, and then you come again to D, then you come again here, then again here, again here, again here, and at some point of time you will jump in here and to the error. So that's what will happen when the control flow graph actually gets evaluated. So the pass which we are interested in will look like this: A, B, C, D, E, G, D, E, G, D, E, G, D, blah, 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 E, D, G, D, and then F in the end. So we're coming to the symbolic execution engine and ask the question whether there is a pass, not specifying specifically the pass, but we're asking whether there is a pass which ends up with F. And symbolic execution engine, they must try multiple passes. So that's how it works. Symbolic execution will just take all possible passes which end up with F, and it will try them all to give it to the solver and ask the solver, does it work? Does it work? Can you solve it? Can you solve it? So it's going to start like this. it will, sorry, it will start like this. It will say A, B, C, D, F. First one. Second one, A, B, C, D, A, B, C, A, B, C, D, E, G, D, F. Third one, A, B, C, D, E, G, D, E, G, D, F. And so on and so forth. So it will take, and then it will go to the solver, and it will say, solve this one. It says, no, I can't solve it. It's not possible. It's not going to happen. This one, no. This one, no. And eventually, it will say yes. Eventually. When eventually? After the pass number 10, probably. Because there will be 10 cycles of the loop, and it will end up with an error. So how much time it will take? I don't know. 1 second here, 1 second here, 1 second, or millisecond, whatever, 1 second, and at some point of time we're going to get the yes. Imagine we replace this 10 with 100,000. Then how many times we're going to go to the solver, ask the question, get the no, and try again, and every time it will going to be slower because the length of the pass will be larger, and that's why the predicate, the pass condition, will be longer. It will be and. Remember, there will be the conjunction of the Boolean expressions. And longer and longer and longer, so the solver will be, the performance will degrade. With every next step, we're going to go slower and slower and slower. So it's called pass explosion, and the amount of pass just explodes just by changing a small number in the code. We just explode the pass from 10 pass, we just jump to 100K pass, and that's unacceptable for the symbolic execution. The problem is called pass explosion. So it's really innocent. The code might look pretty innocent with just numbers here and there, but when you look at the code from the symbolic execution perspective, it's going to explode into a huge number of pass. This collection of pass just grow and grow and grow. It's going to be a large collection of all possible pass. How to deal with that? That's a question which we're going to discuss right now, a little bit later. But I can show you an example, again, using ChatGPT, the favorite tool these days. So look at the code. I gave this code to Clang Tidy. So first step, I gave the code which you just saw. Look at the top of the screen. That's the code you just saw a minute ago. But I changed the number from 10 to 3. So I put the number 3 there. So it's quite simple. The loop will go just 4 times. 1, 2, 3, 4. And when you give this to Clang Tidy, behind the scene is using so-called Clang Static Analyzer. It's quite popular analyzer for C, C++ code. So it tells me that yes, the division by 0 will happen. So it did find the problem. But if I change the number 3 to number 4, then it says, no, I can't find any problems. There are no bugs in this code. So just by changing 3 to 4 in this line will give me, will basically stop the analyzer. So what analyzer will do? The analyzer will just build all the pass, and when there are more than 4, it just stops. It just doesn't continue. It just prevents the pass explosion. So it doesn't go any further if there are more than 4 loops in the cycle. So that's how by default the Clang analyzer works. And then I gave the same stuff to ChatGPT, and I said, you see the ChatGPT, do you see any problems with the C++ code? You see I didn't change this, so I said 10 here, the big number, and it says the loop condition is blah blah blah. So it explains me everything which I just explained to you, and it even suggested how to fix the code. It says, look, change the condition from I equals to 0, equal to 0. It says change this to this. You see, it's very smart, very smart machine, which I have no idea how it works. So you probably have to go to the course dedicated to artificial intelligence and language models. But you see that the ChatGPT actually works with this, and It's funny, you can try it yourself. If you put the number here instead of 10, you put 10 million, which is absolutely unacceptable for any symbolic execution machines. I mean, it's huge. The number is very big, so it leads to a huge pass explosion. ChatGPT will give you exactly the same answer. So ChatGPT does not do symbolic execution. It doesn't care about this control flow graph. It doesn't care about anything. So maybe it just saw this answer somewhere. It just saw this answer somewhere in the book, somewhere in the internet. So it just understands that when the question like this is asked, then it just needs to give the answer like this. I don't know. That's artificial intelligence. I'm not really an expert there. I don't know how it works. Just showing you this for fun. So that's an example of pass explosion. That pass explosion is a problem which unsolvable by symbolic execution in a straightforward way. Straightforward way just leads to huge number of pass, and each pass has to be validated with a solver, and that's it. I mean, maybe there are solutions. I mean, maybe I'm wrong. Maybe there are some optimization here. I'm just thinking right now. So imagine there's a long list of paths, and we see that these paths, they repeat each other, so they have repetitive parts. So maybe we can optimize somehow and just remember the previous answers we get from the previous solving, and we don't solve this part again, because these expressions, they just grow. Every second expression is larger than the previous one, if we have this code for the analysis. So there's monotonically growing, becoming only larger, but every time the left part of the expression remains the same. So maybe we can somehow optimize that. But still, if the number is that huge, then I don't know whether optimization. And again, if you give this number to ChatGPT, it's still gonna give you a good answer. It's still gonna say, yeah, there's a bug, but which symbolic execution engine can handle that? I don't know. So now you know what's going on, and let's still try to use Clang to find the bug in our code. It is possible. Actually, we can do it. Let's use Clang static analyzer, which is used by Clang Tidy, but Clang Tidy is using it with the default parameter. It says only 4 times you loop, only 4, not 5, only 4. That's why it works for number 3, but it doesn't work for number 10. You can change that if you use directly Clang static analyzer. Look at this. This is the code which I give to it. Then I run Clang. Clang says no answer. I mean, it doesn't report any errors. Then I run Clang static analyzer, Clang blah blah blah, and I set the parameter here, the parameter to the analyzer, which is called analyzer max loop. That's a configurable parameter. And with the number 5, it still doesn't give me any errors. But if I say 15, then it reports, boom, I found an error, division by 0. So it's a configurable parameter. And of course, if you put here 10 million, and you give here the parameter 10 million 1, then it's going to give you the division by 0. But how long will it take? Try to experiment with that. See how fast it's going to do this analysis. And pay attention to this line. Pay attention to this. It is, you remember the name? It's the solver, Z3. So this is the solver which we are asking this analyzer to use. Again, I'm not really an expert what's going on, but as far as I understand there, that Z3 is the solver, which is already built into the Clang static analyzer. And here we just point out that it needs to be used during the analysis. So you see, the analyzer is not a solver. The analyzer doesn't solve. The analyzer just prepares everything going through the graph, prepares the expression, the pass constraint, this predicate, and then it gives this predicate to the solver. Solving, it's a completely separate problem. It's a completely separate task, and the analyzers, they don't do that. That's difficult. I mean, maybe it's not as less difficult than analysis, than going through the graph, but it's different. So if you want to create your static analyzer and you want to do symbolic execution, then you will just use some solver. You don't need to create your solver. You don't need to resolve this to solve these expressions. Your job is just to build the expression. It's just to build this pass constraint. And to somehow maybe optimize the number of these constraints which you're going to feed to the solver. Look at this example. So if you, for example, can create a static analyzer which will somehow resolve this, somehow optimize this massive amount of pass constraints in case of this pass explosion, then it's going to be quite interesting, I think, achievement in the area of static analysis. Because look, Clang static analyzer, it does what it does. It doesn't optimize, it just stops. I mean, maybe internally it does some optimization, but it stops. By default, this is the number, which is quite low number, if you can, I think you would agree, because number 4, it's just quite small. So if the loop is longer than, is doing more than 4 loops, four cycles, then we're done. Okay, test. We have 2 more topics and then we finish. So test generation. What is really in practice used for? This symbolic execution. Not only to find bugs. Another thing which is used for is for generating tests. When you have a code, look at the code on the left. I mean, let me describe the problem in general. The problem is this. You have a code in front of you which you wrote as a programmer, or somebody wrote as a programmer. And then for this code, we want to create a unit test. A unit test which will, I mean, the code is already covered by unit test. Let's say your code on the left, this one already has a number of, it's the same code, you saw it before. But this one is compiled and runnable. So you can compile it, you give the parameter on the, it's a C code. You give the number on the input string, on the command line input, and it calculates the result and returns it as a code, as an exit code. So now we ask ourselves whether this code is covered by unit tests, so whether the code is tested enough so that this situation is also covered. So usually programmers, when they design the software, they write code the way they write, and then they create the unit tests which are not covering all possible scenarios of the code. So not everything will happen, not every branch will be taken by the test input. Because programmers are lazy, because they don't have time, because they don't care, for many reasons. So we want automatically to make a tool which will look at the code and automatically generate the tests which are missing. It will just generate the tests with such a combination of inputs for our function, such that we run these tests and now we have the full coverage. Now we know that every X is used, that every necessary X is provided, such that the function goes through every pass, every feasible pass inside the function. So how we do this? This is a tool called CLI. It's just one example I'm giving you, one tool which exists on the market called CLI. It's for C++, C++. So this tool, we take the code on the left and we transform into the code on the right. So we add this line and we add this line. So instead of actually taking the real inputs from the real, when the real console, when the code is executed, we remove this. So I take it away and we say this is a symbolic value. And then we run and then we compile this. The code on the right we compile. We compile into LLVM bitcode, not in the binary code which is executed by the machine, but we compile into a bitcode. The bitcode is it's like an internal representation of the code in LLVM. About LLVM we discussed before. It's a virtual machine. That's why VM. It's a virtual machine which has its own language inside called LLVMIR, and its language may also be represented in form of a bitcode. The bitcode, like a binary representation of the code. So we ask this tool CLI to take this code and compile into the bitcode. We do all of this in order to generate new tests, because let's say this function is very complex and we don't know what is the right X to provide. So we know that we can provide 0. The programmer already wrote the code and 0 is provided. So when I provide 0 by the unit test, then the function is executed and it returns some result. But I'm not sure that this is a full set of all possible inputs that are enough to test all feasible paths inside the function. Apparently it's not. We know about this. We know that there's number 2 must be provided as well. So there are at least 2 inputs which must be given to this function in order to say that it is fully, exhaustively tested all of its internal feasible paths. CLI can help us on this. Like I said, we instrument the code, so we change the code. Now it's not exactly the same code. We change the code outside of the function. You see, we don't touch the function itself. The function is untouched. It's exactly the same code. We didn't touch it. We only change the way we call this function. So now we say it's a symbolic function, and then we compile this stuff into Bitcode. Remember, not to the machine code, but to Bitcode. First line, it compiles Clang, then I provide the input string, then it's this one says compile to what we ask. This is for debugging. Then we say emit LLVM. I think this C is the marker for the Bitcode. And then the no optimization here, and then we provide some parameter. For the Clang itself, I'm not really sure, but this one I got it from internet, but it works. I tested that, so this is how it works for me. This line works for me. Then I run the CLI. So first it was the compilation done by LLVM. It's normal compilation of the code already instrumented. Then I run this tool CLI. The CLI executes this code. It's not executing it. It's doing symbolic execution. So it doesn't run. You see A, B, C. BC is the extension for the Bitcode. So this code is not being executed by the machine. It's executed by CLI. So CLI goes through the Bitcode, imagining that the code is being executed, and does everything we discussed before. It does everything we discussed in the symbolic execution theory. And it says, we found 2 paths. The tool found 2 paths and it generated 2 tests. And if we see what's generated in the directory, you will find 2 files. They're quite small, like 46 bytes in each file. So they're really small files. These files are just binary in their format of the CLI. I don't know why they do it this way, but that's how it works. So they kind of found 2 paths and they suggest 2 tests. They suggest that these 2 paths, they're both feasible, and they know how to run through these paths, what is the right input for the function f in order to go through this path. You can actually run this one as well to see exactly what is inside the Bitcode if you want. There is a long description of this code. That's the CLI workflow. Then let's take a look at the tests which are created. So again, remember this is our code. It's a little bit smaller now than before, but I can scale it up. So let's see what's in the first file. This is the first file generated by CLI. This is the internal. So this CLI tool is actually printing what's there. Just a log tool to show us what's inside. So it says, okay, the variable I found the variable x in the code. The size of this variable is 4. It's a size of bytes. The data which I suggest to provide is this. So this is actually number 4, which we were looking for. This is int, you see. So it suggests that number 2 is the one you need to provide. And another one is number 0. So it did what we wanted. It found 2 numbers. This is number 0, and this is number 2. So it found 2 numbers. 0 you provide, you get 1 pass. The number 2 you provide, you get another pass. If you give it a larger function, more complex, with more if, then, else, loops, and everything, try it out. You will see how many of these paths it will be able to find. But that's a practical application of symbolic execution, not to find the bug, but to help us generate the test. Because if you now know these 2 numbers, 2 and 0, you can easily generate a C++ piece of code, which you can call unit test, and this unit test will just send the number to the function and expect it to, I don't know what to return. We don't know what's going to be the expected result here, because it's outside of scope of symbolic execution, but at least it will run it and the pass will be covered. So it will help you to add pass coverage. And you can replay these test cases. So this is the scenario. How can you actually, using these test files, if you don't want to write the unit tests using the numbers, you can just use the k-test files to run your application. Then how we do it, first we recompile the code to create the actual binary code now, and then you run this binary on a real computer and check what is the output. And you see that the output for the first test is this, the output for the second test is that. That's it. That's the test generation, where symbolic execution is the key ingredient. And finally, the last point is concoling testing, so-called. Concoling, it's called because it's a combination of two words. So it is concrete plus symbolic. Concrete plus symbolic. You get concoling. It's a funny name, and I will explain you now how it works, what it's for and how it works. I think it's quite interesting. So look at this. That's an example to motivate you for finding a solution. On the left, you see the code. Read it. The code has, first we define the user. The user is enum. It's C++ code. So it's enum, which is 4 possible users. Okay, it's a toy example, but still. Vicky, Peter, Jeff, and Sarah. And then the function salary of the user. So the function salary of goes to the database and returns you the salary of this user. We don't know what's in the database, but a number will come out of the database. Well, we know what's in the database. This is what's in the database. These are the numbers which the database contains. And then we have a function raise. The raise function, you give the user and you give the limit. So the function checks the salary of the user. And if the salary, the actual salary, is less than the limit, then the update will happen. So we're going to increase the salary of this user. Very simple. Now we want to write a unit test, actually all unit tests for this function, such that all possible feasible paths are covered. So we want this to happen either left or right. So let's be more as practical as possible. So we basically want 2 paths to happen. The path number 1 is when the salary is increased. The path number 2 when the salary is not increased. So how do we do that? How can we automatically suggest these 2 numbers? What's going to be the user for the test? Let's say it's going to be, what is the user and the number? User and the number. So we need to provide 2 pairs. How to find them? How can we automatically create a software which will find it? If we go through a symbolic execution, which we discussed before, then it's going to be like this. So we draw the graph, we create the control flow graph on the right. The first line is salary, S is equals to salary of U, and then S is less than limit. And then we're going to come here with the symbolic state 1. This is symbolic state, and this is symbolic, and this is the pass condition. Pass conditional one. So now let's give this to the solver. Let's ask the solver, okay, give us the solution. What is the solution? So that we end here, it means that this is going to be the question to the solver. S is less than L. And they're both symbols. S is symbol, L is symbol. So what's going to be, and S is a salary of U. So the executor, the solver will get this salary. Okay, this function, this magic function, salary of U, it's a symbol, less than L. So there are 2 symbols, symbol number 1, symbol number 2. Okay, give us the answer. What is the answer which the symbolic execution, the solver can give us? It's not possible because this function, this salary of, is unresolvable, or almost unresolvable. It's not possible for the resolver, for the SMT solver, to come up with the solution. So what should be U? Is it going to be Jeff? Is it going to be Vicky? What are the numbers? The answer is, I don't know. The answer is, I don't know. And that's it. And we stop here. Because we cannot teach the solver to reverse this function salary off. That's dead end. The solution is concoling testing. How it works. There are two steps. Step number one, what do? Step number one, we do a concrete, that's why it's concoling, concrete and symbolic. The first step is concrete. We take a random input to this function and run it on a real computer. Not symbolically, but really. So this is the random input, Vicky 0. We just select why Vicky 0, because remember, this is the Vicky, this is what we have. I mean, this is the enum. So we take Vicky and we take its integer, so we can take 0. Right? We can do that. I mean, it's a first random number, first random input, Vicky and 0. Then we run it physically. What will happen physically is that we're gonna go to the database, the actual call to the database will return here number 120. It's the actual salary of Vicky, and it will say, okay, user is Vicky, limit was 0, S returned was 120. And it will fail here. I mean, there's going to be false, so it's say, okay, no increase, so we'll go by this pass. And that's it. We stop here. We just know that happens, and we know that for this input, for Vicky 0 and for Vicky and 0, we get 120. And then we go to symbolic execution, and we already have the first test. We already have Vicky 0, 1 pass is feasible, we get it. We don't need symbolic, we have real execution, we have real numbers, and we know this is one way to test this function. Now the question is how to find a second way or more ways. And we know that there is a second way because we remember that there was a condition here. And if there was a condition, then it means it's a branch. It means it's a two directions, two possible ways to go. So we go on the symbolic execution. We neglect the condition. We invert it from less to more than. And we understand that if we revert this condition, then definitely the execution will go through a different pass. That's going to be another feasible pass. So the question is how to revert this condition. And now the problem is much simpler because we know that in this condition, in order to arrive to this place, we still remember the formula, S is less than L. But before, in this S here, we had a call to some magic function S in the database, right? It was the call to the database, the XScale database. Now we can put the actual number here, taken from our experience. So our concrete execution experience allows us to put the real number into this S and say, this is the information we already have. So this 120 can stay here, and we know, let's put it this way, we know that in this condition can be inverted. Hold on. This condition can be inverted by either by changing one of the ingredients of the condition. And there are two ingredients, the S and the limit. So we can, using our experience, we can fix one of these ingredients and keep the second one as a symbol. Maybe I'm not explaining it correctly. But let me try to on a more, maybe a bit higher level. So with the concrete execution, we collect the numbers which allow us to simplify our symbolic conditions, our past constraints. So past constraints are complex because they have things which are unresolvable, which depend on like the functions which are out of our control. In order to remove these dependencies, we use concrete execution, which allow us to place constants, to place fixed numbers into the formulas. Before, the formulas on the left side, before a concrete execution, the formulas were completely symbolic. Everything is a symbol, and the links to the outside world are unresolvable. When we run, then these links to the other outside world, they are resolved, and they allow us to put the constants in the formula. When we have the constants, then we can more easily resolve the symbols. Then we can say, what is L here if L is just more than 120? Okay, 121 is a good solution. So now we can have, here we have V key 0. This is the first pair for the unit testing. And this is the second one, V key 121. Another pair. So look at the data in the database. V key 120. So definitely V key 0 will increase the salary. V key 121 will not increase the salary. So that's it. We found two good combinations for the input by using this Concoling so-called testing. Concrete execution, using these numbers as constants in the formulas, neglecting the condition, all the conditions, or first one by one, neglecting the condition which guarantees that the pass will be, the execution will go on a different direction as it was before, on a different path, and then using this knowledge, we resolve the conditions which are left. We try to do it, and then we resolve if it's possible. If it's not possible, we again execute. So it's like execution and symbolic, concrete execution and symbolic, and again, multiple times. And that's how you find many more test inputs. So that's it. It's good we write on time. I suggest some reading. I just found really good GitHub repository, which gets together a lot of information. There's actually almost everything which you need to know about symbolic execution. So I suggest to start from there. You will go from there to a number of lectures, a number of papers on that. In my opinion, it's not really a complex topic if you stay on the entry level. Of course, if you go deeper and deeper, then you can get much more higher complexity, and there's a lot of research there. But to enter into this area, I think it can be done in just really in a few days. All you need to do is really good control flow graph, which represents your program, and then you start going through the graph, and you need a solver. So you need SMT Solver, which you can take existing one, and you can maybe use existing software to generate control flow graph. Then you combine them together, you get a symbolic execution, which can, for example, be a new test generator. You can create it, or you can create static analyzer, which will find bugs, and something like that.